In the first lecture, I introduced the basics of the Schrödinger formulation of quantum mechanics, including the key notion of a wave function. This is the most commonly used formulation of quantum theory, and we're going to use it throughout the course. We're going to discuss in great detail the interpretation of the wave function and properties of the Schrödinger equation. But today, I would like to give you an idea about an alternative formulation of quantum theory using so-called Feynman path integral, which in my opinion is a very beautiful formulation of quantum mechanics due to Feynman. I should mention that this material is almost never taught, at least at the undergraduate level, and when it is taught, it's usually sent towards the end of the course. But today, I will experiment a little bit with this material and will introduce it right away. And one of the goals here is for me to tell you that what you read in regular textbooks, and actually here in this course, is just one way to think about quantum physics, the most commonly accepted way to describe quantum mechanics. But there are many other ways, actually. Some of them don't even include the notion of a wave function, and you should be aware of their existence at least, and keep an open mind here and actually in general whenever you study science. The derivation that I'm going to present later in this segment follows very closely this paper by Richard Feynman. Well, a part of the paper is much more detailed, written back in 1948. This paper is a typical Feynman. So if you read the abstract, the first sentence of the abstract says, non-relativistic quantum mechanics is formulated here in a different way. So he suggested a completely new way to think about things here. Now, I should mention that, well, notice the date, 1948, so this time was actually a very difficult time for Feynman. So there is this book which I would recommend for you to take a look if you're interested in Feynman as a person. Perfectly Reasonable, it's called Perfectly Reasonable Deviations from the Beaten Track. So this book is real. There is no shortage of books about Feynman, but this book is pretty much a collection of letters that Feynman wrote throughout his life. When you read this book, when you read these letters going back to this period, to the 40s, you see that it was a very, very painful time for Feynman because his wife Arlene died at the high school sweetheart whom he married died in 1945, in June of 1945 of tuberculosis, and he was it was not easy for him to deal with this. So the latter sort of buried this feeling very closely, and despite this difficult time and maybe suffering and some sort of desperation, so he came up with a number of very influential, very original, very unusual ideas, and one of those ideas is this path integral, actually. In any case, going back to the actual physics, so I'm going to present the derivation. But, and as I mentioned, this derivation is rarely introduced in the very beginning of a quantum mechanics course. And one of the reasons here, of course, is that technically it's actually quite involved. And furthermore, the end result of this calculation is actually a new mathematical object that hadn't even existed before Feynman wrote it. And after he did, mathematicians have been arguing to this day about its precise meaning. So there is some technical issue, there are some technical issues which exist, but for those of you who are not really interested in these technicalities, again, I just would like to briefly tell you the main ideas without going into math. So let us consider a quantum particle localized at the initial moment of time t equals 0 in the vicinity of a certain point, initial point r sub I. And let's ask the question of what is the probability for this particle to reach a final point r sub f in a time t. So if it were a classical particle, it would have followed a unique, well-defined classical trajectory. Let's say for a free particle, it would have been just a straight line connecting the 2 points, but in general, it would have been a solution of the second Newton equation or the Lagrange equations, but it would have been a unique classical trajectory. So the main result of Feynman in this paper is that in quantum mechanics, the particle goes over all possible trajectories at the same time in some sense. So it follows the classical trajectory, this trajectory, any trajectory you can imagine. And there is a weight, a complex weight associated with each trajectory, which is the exponential of I times classical action divided by the Planck constant. So classical action here, we're going to discuss it in more detail later, but just to remind you, the classical action is an integral from 0 to t of the Lagrangian, which is the kinetic energy, basically mv squared over 2, minus the potential energy times dt. So this, in classical physics, the minimum of this action gives rise to Newton equations and to classical equations of motion. In quantum mechanics, there is no principle of least action, as Feynman showed, but all actions are allowed, and all of them give rise to some terms in quantum theory. Now, going back to the probability of going from the initial point to the final point, in some sense, this probability can be represented as a sum over all, well, the absolute value squared of a sum of all possible classical actions over all paths that I label here by an index L. And this sum itself is essentially symbolically represents what we're going to see as a path integral, which will come out of the theory naturally, and it's really a very remarkable result. Now, it turns out that, again, so the mathematical part of it is quite subtle, but one can actually solve some problems just by using this sort of cartoon picture of what a path integral is. And I'm going to give you an example of such a solution. So even if you don't follow very closely and carefully the derivation of the mathematical formalism, you can still follow the main results, the main qualitative results later on.